Okay, so I think we can start. So what we are going to do, not today, but perhaps throughout this week, is review the fundamentals of probability and statistics, because for studying reliability we will be needing that. So it will be more like a refresher course. But before that, how many of you have done prob and stat, a course on prob and stat before? 1, 2, 3, only 3. How many of you are the UG? UG has done, I think, APL 101. There was some prob and stat there. I think that should be enough. So, including 101 and prob and stat separately, let us say MTL, and your UG course, let us say in UG you might have done if there are masters and PhD. So, how many have never done prob and stat? Is there anyone who has never done prob and stat? No, right? Okay. So, then we are good, okay. So, what we will do is that, as I said, we will be reviewing very quickly the concept of concepts associated with probability and statistics, the basic concepts which we will be requiring for this course on reliability and reliability based design. Okay. So, that is basically the idea. So, with that background, let us start, and as I said, we are reviewing it. So, I will not define things in a formal way, rather I will try to explain and remind you about aspects and concepts through examples mostly. Okay. So, to start with, in probability and statistics, we start with a random experiment, right. So, let us take the concept of tossing a coin. So, tossing a coin, can we call it a random experiment? We can call it, right. Why is tossing a coin a random experiment? The outcome is not fixed. You cannot predict the outcome with certainty. So, a random experiment is basically an experiment where we cannot predict the outcome of that experiment with certainty, right. So, that is a random experiment. So, let us take an example. Let us take an example of tossing a coin. Okay. There is some issue here, it seems. Let me see. So, okay, there is some serious issue, it seems. So, let us consider an example of tossing a coin. Okay. Let us take an example of tossing a coin. Now, what are the outcomes? Head or tail, right? Head or tail. Now, but before I go there, let us consider this, right. So, there is a thing we are talking about, which is tossing a coin. So, tossing a coin, this is my random experiment, right. So, first of all, we focus here, and this is my random experiment. And whenever there is a random experiment, I will have an outcome. Any experiment I will have an outcome. That outcome I might be able to predict, I might not be able to predict. In random experiment, I will not be able to predict with certainty. I might be able to predict with certain probability, right. So, for a random experiment, there is a outcome. Okay. An outcome of a random experiment is called, what is it called? Event. Exactly. It is called event. Okay. So, outcome of an experiment, random experiment, is called event. Correct. So, in my case, or in our case, the event is either head or tail. So, that is my, at least for this small example, that is my event. Now, there is one more concept all of you are aware of, let us see, sample space. What is sample space? Collection of all events, you are all aware of, right. So, the sample space is basically collection of all events, collection of all events, right, all possible events, that is known as the sample space. Now, let me try to fix it. Okay. There is some issue that is happening which is prohibiting me from writing over the whole screen. App here. Now, it should work. Hopefully, it should work. Let us see. Yes, much better. Okay. So, sample space is collection of all events, right. Now, we have defined random experiment, sample space, and all of this you are aware of. How will you define probability? What is probability? What is probability? How can you define it? What do you understand by probability? So, anyone?
What are the chances of an event happening out of all the events possible?
Chances, that is correct, but chances you can think of it as an synonym to probability maybe. So, chances is correct, but there is something more. It is a numerical value quantifying the chances, right. It is a numerical value quantifying the likelihood of an event. So, the important point here is that it is a so the so probability, it seems I cannot use my Mac from next class, I have to bring my Windows. So, the probability is basically a numerical value quantifying the likelihood or chances of an event. Okay. And this is again, you were at least aware of this by intuition, you had the intuition of what is probability. But have you heard of Kolmogorov's axioms of probability? I am sure you have heard of it, but have you heard of the name? So, how many axioms are there? 3, correct. By the way, it initially started with 5 if I go to the history, and then it was cut down and brought down to 3, right now it is 3. So, there is this Kolmogorov axioms of probability. So, what are these axioms? What is axiom 1? Correct, non-negativity, right. So, we are talking about Kolmogorov's axiom, and very quickly the first axiom, as you correctly said, is non-negativity, which means that probability of an event cannot be negative. That is the first axiom. What is the second axiom? Probability of sample space, and that is a name, it is known as the normalization. That if there is a probability and if you take it over the sample space, that is you are kind of normalizing it, you should get 1. Okay. So, the second axiom is about normalization. Okay. The second one is about normalization. What is the third one? What is the third one? Always disjoint. So, that is known as the additivity, additive, right, additive nature. So, the third one is additivity or additive nature, whatever you want to call it, and that is that for two disjoint events, the probability of these two, the union of the two events is equal to the sum of the individual probability. So, probability of A union B is equal to probability of A plus probability of B, assuming A and B are disjoint, right. So, that is basically the third property. I am not writing those because you are aware of those, but I am just kind of trying to remind you of these terms, right, because we will be needing it at some throughout this course actually, not at some stage. Okay. So, these are the three axioms. Using these three axioms, we can come at the arrive at the law of probability. Okay. What are the law of probability? There are two, I mean some people say three, but I will say two primary law of probabilities. One is the sum law, the other one is the product law. So, there are two laws of probability, one is the sum law and the other one is the product law. But before I go there, I need to define conditional probability. Okay. I need to define, so I will come back to here, but before I go there, we need to define conditional probability. Okay. What is conditional probability? Someone? What is conditional probability? It is, I mean I am not bringing in dependence right now. What is conditional probability?
Calculating probability of an event given another event has already occurred.
Give me one example, that is correct. One example, I'll let me give one example, right. So, suppose you wake up one fine morning, okay, and your windows are closed, so you do not know what is happening outside. If I come or call you and ask that what is the chances, that is what is the probability that it had rained last night, you will give me some number 0 to 1, it will vary somewhere between, or 0 to 100%, some numbers you can come up with, right. So, that is your belief about the fact that it might have rained the last night, correct. That is probability of an event that it rained yesterday night. Okay. And remember, you were sleeping, you just woke up, the windows were closed, and so yeah, so that is why you did not know anything. So, now I tell you that okay, you have told me something and that is fine. Now, you can open the window, check outside and then tell me. And then you open the window, you checked outside and you saw that the grass is wet. So, this grass being wet, we can call it as a second event, let us say event B. The first event was that whether it has the rain was there last night or not, right. And the second event is whether the grass is wet or not. Now, what will be the conditional probability? The second one, probability that it was raining yesterday night conditioned on given that the grass is wet. So, it tells about your belief regarding an event after you have observed some other event, and these two events might be related, might not be related, and I will come to that. Okay. So, this basically tells us about event, about an event A given event B has occurred. and this we denote as probability of A given B. Okay. So, whenever you see this A given B, remember that the event B is no longer random. So, it is random whether the grass is wet or not, but you have observed it. So, for any random experiment, the outcome is random as long as the experiment has not occurred. In a coin toss example, you do not know the outcome as long as you have not tossed the coin. The moment you toss the coin, you know whether it is head or tail, and that is certain, that is deterministic. So, whenever you see this given, remember that B is a random variable, but in this case you have seen the event B. So, you have either found out that the grass is wet or you found out that the grass is not wet. So, that part you should be very clear about, that whenever I am conditioning on, it is still a random variable, but it is conditioned on some value. So, some value has been observed, okay, and that is a common confusion that I see among many. Okay. So, this is my conditional probability. There is another probability which is the joint probability. In this case, can you tell me what will be the joint probability? The joint probability will be that it was raining and the grass now is wet. So, now it is no longer that you have observed the grass is wet and now you are trying to infer what is the probability. It is that you do not know anything, but the grass is wet, what is the probability of that, and it was raining. So, the other one is the joint probability. Okay. And this you denote as probability of A. So, I will write in this manner throughout, but this basically means A intersection B. Okay. So, this basically is nothing but is equivalent to probability of A intersection B. So, this means that event A and B occurring together, okay, occurring together. So, this is basically my joint probability. Okay. So, now how can we relate these two things? Okay. Let us take one example and see, a very small example. Okay. So, let us take an example where I have two things. One is that I have a dice. I can throw the dice. The outcome will be varying from 1 to 6. I also have a coin. I toss the coin, and the outcome can vary from heads or tail. So, I can draw a table like this. Okay, where the first row is, let us say, getting 1, 2, 3, 4, 5 and 6. So, this is basically the columns are representing what is the outcome when you throw the dice, and the rows will be representing head and tail. Okay. This is known as the joint probability distribution table. Okay. This you can only do for discrete, by the way, but this is known as the joint distribution table. Now, what now each of these elements will denote? So, what will this denote? Can you tell me? Head and 1. Okay. Similarly, this will be head and 2. This is tail and 3, and you can think that there will be 6 cross 2 boxes. Okay. So, let us take the fourth one. Okay. And let us call it, so actually it is what? Probability of, let us say, 4 head and 4, right. But if I generalize it, I can call it probability of ith and jth event occurring together, right. And not only that, I will not write probability here. I do not want to write probability. I will write here, or rather I can write probability. Let me write probability. Okay. I can also count. I can write the count also. That is what I was thinking. That instead of probability, you can write the frequency. You have done experiments and how many times you have observed what, right. So, this is your probability of h comma 4, right. So, in a generic sense, what will be this probability of h comma 4? Number of times you have observed h comma 4 by number of experiments. So, if you perform 1000 experiments, you will count how many times you have observed this combination of head and 4, and you will note that number, and then you will find out the ratio, simple, and that will be your probability of head comma 4, right. Now, if I ask you what is the probability of head given 4 has occurred. So, suppose I want to find out probability of head given 4 has occurred. So, that is the answer. I do not want the answer. I want to derive something, okay. That is correct. So, think about it. So, first of all, what will you do? You will first count how many times head and 4 has occurred together. First, you will count that. So, number of times head and 4 has occurred together. You have done 1000 experiments, and then out of that you will basically find the ratio with number of times 4 has occurred from the basic intuition or definition of probability, right. So, you have done 1000 experiments, you will first count how many times that both of this has occurred, that is your n h comma 4, and then you will see, okay, out of those how many times only 4 has occurred, and then you will find the ratio, and that is basically your probability of head given 4. Now, what I can do is very simple, n h comma 4 divided by n multiplied by n divided by n 4. Now, what is this n h comma 4 divided by n? p h comma 4. So, this quantity that you are seeing is probability of h comma 4, right, and the second quantity you are seeing is 1 by probability of 4. So, that means you knew this already, I know. So, that means if I go here, this is equal to probability of A and B occurring together divided by probability of B, and this is a formula you are already aware of, nothing new. I mean, everyone, I mean, you do not even need engineering for that, I think in your school you have done this, right. So, you are aware of this. Okay. So, we have the joint distribution, we have the conditional distribution, and we have the relation between the joint and conditional distribution. Now, remember, I will go back to the law of probability, but before that one more concept I want to touch upon very quickly, which is the independence of event. So, there is this A and B events, right, and what was A? That whether it has rained or not. What was B? That whether the grass is wet or not, in our case. But in generic there is this event A and B. When will you call these two events independent? So, someone was talking about dependency. So, when will you now call these events independent? Not the equation, from a theoretical point of view. There are two events, random events or events outcome of a random experiments A and B. When will we call these two events independent? When do we even call two people independent? When one person does not influence the other. That is the basic definition of independence, dictionary definition, right. So, even in this case, what should it be? That your one event should not influence the other, right. So, if that is the definition we are going by, or if that is the, so independence, and we said that A does not influence B. That is what we talked about, right. So, now if that is the case, what does it even mean from a probabilistic point of view? It means that it should not matter whether you have observed A or not. Your belief about B will remain unchanged or same. So, this means probability of B given A should be equal to probability of B. It means if these two events in our example they were dependent, but if these are not dependent, they are independent, then it should not matter whether that event has occurred or not. Your belief will not change. Correct? It should not change. For example, suppose there is another faculty taking a class, whether that faculty is present in IIT Delhi or not should not influence whether I am going to take a class or not. So, these two are kind of independent events, for example, right. So, now let us take one example. Suppose I have a coin, okay, and I am tossing a coin. Event A is that I will get a head. So, getting a head is event A. Event B is that I will get a tail. Okay. Now, will you call these two events independent or not? How many of you think independent? Raise your hand first of all. Is there anyone who thinks they are independent? You think it is independent? Why? No, remember I am tossing the coin only once. I did not say I am repeating that I did not tell. So, is it independent or dependent? Okay. So, I am guessing everyone believes it is dependent. You think it is independent? Why?
Because we don't exactly know. We don't know exactly whether it's head or tail. So
No,
we can say
that is a definition of random experiment. I mean, we don't know is random. Independent is one event should not influence the other.
they won't influence
They won't influence.
appearing of either head or tail.
Okay. And others think it will influence, right?
Depends on the conditions.
How?
A is we are given that A is the event only it is getting ahead.
A is getting an head, B is getting a tail. So, you are saying that it depends on condition. What condition? This is the only information you have. There is no other information given.
That like we given that if tossing is again and
I already told it is only one toss. I already clarified.
one event if it is a complementary then if it is tail then it has its head obviously.
So, is it independent or dependent is the question. Those history lesson will come later, but right now whether it is independent or dependent. You are confused basically, let us put it that way. Others are saying that it is dependent. Why? If head has occurred, then probability of tail is 0. They are mutually exclusive, so that is correct. So, I will come to that. Actually, I want to relate that to independence to be more honest. So, if head has occurred, then tail will definitely not occur. So, that means it is not only dependent, it is strongly dependent. It is giving you a certain event. 0 and 1 are the strongest possible belief you can have. 1 means it is definitely happening, it is no longer random. Same with 0, it is definitely not happening. So, if A has occurred, then definitely B is not occurring. Whereas, if A has not occurred and let us assume the coin is unbiased, then B might occur, might not occur. So, your belief about B is definitely getting changed if I tell you that A has occurred. I have tossed the coin and put it inside some box which is not visible from outside. And if I ask you what is inside that, you will say okay, it can be head or tail. Let us say it is unbiased 0.5, 0.5. I showed you it is head. You will say okay, then it is not tail. So, that is why they are dependent. Mutually exclusive events are always dependent. because in mutually exclusive events, if one happens, the other will definitely not happen. So, it is not about that whether head and tail or not, you have to think about it holistically. Okay. So, keep that in mind. Okay. Okay. So, A B given B given A is equal to probability of B, that is the definition of independence. And similarly, obviously, if this is happening, the other will also happen, which is probability of A given B is equal to probability of A. Okay. That will also happen. Okay. So, now let us come to the most important part, two of the most important part. First one is the laws of probability. Probability. The first one is the, let us write the product law first, that is the easier one. Product law. And what is the product law? Are you aware of the product law for probability? Can someone tell me? What is the product law of probability? I have already written it in the previous slide, that is a clue. Probability of A intersection B is equal to P of A multiplied by P of B given A. This is for two events, you can generalize it to n number of events. So, product law is basically probability of A, B, which is A comma B, which is A intersection B, whatever you want to write it, probability of A multiplied by probability of B given A. Okay. This is for two events. What will happen for n number of events? Probability of x1, x2, xn. So, can you tell me what will it look like? x1, then x2 given x1, then x2 and x1, and this will continue. Okay. So, basically probability of an, let us say the ith one given 1 to I minus 1, and that will go on. Okay. So, this will be equal to probability of x1, probability of x2 given x1, probability of x3 given x2 comma x1, and then dot 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 probability of xn given x 1 to n minus 1. Okay. So, I wrote a shorthand representation of x1 comma x2 comma x3 comma dot 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 comma xn minus 1. Now, this is very important, and there are, we will not talk about it in this course actually, but let me quickly tell you that this kind of expression is very important and very useful in machine learning. For example, there is a whole idea of this Markov process and Markovian assumption and all of those things, that is based on this kind of representation. In Markovian, what we will do is we will assume conditional independence. x3 given x2 comma x1, we will assume that that is equal to x3 given x2. You will assume that, and that will basically, so basically it only depends on the previous, and the others are becomes conditionally independent. Okay. So, this expression is very important throughout this course, but also in, let us say, machine learning, for example. Okay. Yeah. This is the product law. Okay. You are aware of it, nothing new. Sum law. What is the sum law of probability? Sum law I have not shown, I have not written. A? No, that is not the sum law. A, probability of A plus probability of B minus probability, that is not the sum law. What is sum law? No, that is, then why is it a law? That is an axiom. That was the second axiom, right? Sum law is actually related to something known as marginal distribution. So, probability of A is equal to summation over B probability of A comma B. Okay. Probability of A is equal to summation over A comma B, and if I go back to the table, can you tell me there were 12 entries, right? Each of these entries would have been 1 by 12. if I assume everything to be unbiased, right. So, suppose I ask you what is probability of head. So, you can sum over those 6 1 by 12s and you will get 1 by 2, and you already knew that probability of head is 1 by 2. If I ask you what is probability of 1, you will sum over the column, that is basically give you 1 by 6, 1 by 12 plus 1 by 12. So, that will give you 1 by 6. So, that is the sum law. So, that means if you have the joint distribution and if you want to find distribution of a given event, you just sum over the other event. This has many names. One of the popular names is marginalization. When you say something has been marginalized, whether that is there or not there does not matter, you kind of average it out. So, in this case you are basically doing an addition over B, so now B is not there. That is why you have marginalized out B. Okay. So, this is basically, and by the way, if you do that, then probability of A is also known as the marginal distribution. Okay. Because if you have a joint distribution, if you are finding out one of the variables distribution, that is known as the marginal distribution, and this process is known as the marginalization. Okay. This is known as the marginal distribution. Students, I have given you a sheet, circulate. Okay. By the way, that reminds me that Accordly, I think I have registered, you might have received the email, so we will use that. So, please give your attendance there today. I am also taking a paper attendance because I want to check whether it is working perfectly or not. It is the new thing, right? I need to check it. Okay. So, yeah. So, I think you received an email, and those who are new, you have received email from 7900, others have received email from 871. Okay. So, I think the website is app.accordly.com or something like that. Okay. Probability of A is basically known as the marginal distribution, and this process is known as the marginalization. Okay. Now, remember this marginalization has another name that is not obvious right now, but this will become obvious if I go to continuous random variable, and we will define what is random variable in a while. So, this marginalization is also known as, or the process is known as integrating out, because this summation will become integration if A and B are continuous variable, and then you will say you are integrating out a variable. So, these are very common terminology that are used interchangeably. Marginalizing out a variable, integrating out a variable, all of these are used quite commonly and interchangeably. So, you should be aware of this terminology. Okay, you should be aware of this terminology. Okay. Before I go into random variable, I have 10 minutes, right. Can you think and tell me why or the importance of independence, or rather let me make it more simple. So, suppose I am interested in this event, probability of A comma B. Okay. Now, these probabilities will not be known to me a priori until and unless this 1 by 12 number I gave is based on an assumption that these two are unbiased. But in a realistic scenario, you will not know what is probability of head, you will not know what is probability of tail, you will not know what is probability of 1 or 2 or 3 or 4, or you will not know any of these events, right. So, in that case, these probabilities will be known as, or will be unknown to you. So, those are like parameters that you want to, or that you have to estimate. So, with that in mind, can you tell me what is the number of independent parameters that are there in this example, just for this example? What is the number of independent parameter that you need to estimate? And consider A and B to be generic, and it need not be head and dice throw, it may be dependent also. Okay. So, in a generic sense. So, if you have a table, or if you have an event A which can take, let us say, which has n outcomes, if you have an event B which has m outcomes, okay, in a generic sense, and I do not know whether A and B are independent or not, they are potentially dependent. So, in that case, what is the number of parameters you have to estimate? Nm minus 1, correct. Everyone is on board with that? For anyone, this Nm minus 1 is not clear. Is there anyone? Okay. What is the total number of probability you have to estimate? Nm? That you are on board with, right? Why minus 1? Summation is 1. So, that means independent is Nm minus 1. The last one is 1 minus whatever you have estimated. Clear? Or do you want me to repeat? Repeat. Okay. Let us take this example. Okay. So, I said it is 1 by 12, 1 by 12, 1 by 12 I said, right. So, suppose I know that it is, suppose I know that this is P1H, this is P5H, and I know all of this. That is from 11, right? No, not this. Okay. So, suppose you know all of these 11 boxes, which is P of 1 comma H, P of 2 comma H, 3 comma H, 4 comma H, 5 comma H, 6 comma H, and then 1 comma T, 2 comma T, 3 comma T, and all of this. You just do not know this one. Can you tell me what this value will be? So, that means I do not need to find this out. If I know that everything except 1, that last one I can estimate. So, that means what is the number of unknowns? 1 minus the total elements, because this one is dependent on the other ones. So, I am saying number of independent parameters. Clear what is happening? So, in a table the sum should always be equal to 1. So, since the sum is 1, that is the additional constraint you have, you only need to estimate nm minus 1 number of parameters. Clear?
And the probabilities of each event being called as parameters.
Yes, because in reality you will not know those probabilities. If I give you a coin, do you even know what is the probability of head and tail? When you say you know, you are assuming it is unbiased. So, that is the assumption. That assumption you have to let go of. So, then you start calling them parameters. Clear everyone? Nm minus 1, clear, is the number of parameters when I have not made any assumption. Clear? Now, let us assume that A and B are independent. How many unknown parameters now? Independent. A and B are independent. So, this event A and B are now independent. N minus 1 multiplied by, multiplied or plus?
N by 2 minus 1
Plus. What did you say?
half of that minus 1.
Half.
Nm by 2.
Where is Nm by 2 coming from?
Because head, if it's not head, then it will be tail. So half of the parameters will be known.
The question, did you understand the question? I said event A and there is no head and tail, there is event A and B. Event A has n outcomes, event B has m outcomes, and I am giving you A and B are independent. N plus m minus, that is n minus 1 plus m minus 1 you were saying. You?
No, I didn't got the multiplication by some because it's
I will come to that, but you are saying that it should be multiplied, right? I will come to that, do not worry, I am not giving you the answer, I will come to that. So, one answer is n plus m minus 2, one is n minus 1 multiplied by m minus 1. Any other answer? How many of you think it is n plus m minus 2? Okay. And how many of you think it is n minus 1 multiplied by m minus 1? Yeah, you two I know, you do not. So, let me explain, right. So, remember, we have, this is the definition of independence, remember that, okay. A given B is equal to A. With that definition in mind, probability of A, B, this is what I want to find out, is equal to probability of A, probability of B given A, and because they are independent, this will be equal to probability of B, and this is the well known formula everyone knows. This is actually, if I ask independence, this is the first thing that comes to your mind, not the conditional one. This is what comes to your mind, right? So that means you need to characterize this event and you need to characterize this event. If you characterize this event by multiplying them, you can find out the other probabilities, but you need to characterize only A and B. A in our case was tossing a coin. So for tossing a coin, how many parameters do I need? 1. Probability of success, probability of head. Because if I know probability of head, I know probability of tail. 1. B was throwing a dice. Correct? How many parameters do we need? 5. So what is the total number of parameters? 6. But you can, using this 6, you can find out those 12 entries. So you are going for the entries, but those entries are now not independent. They are getting multiplied. So by multiplying this, you are getting those 12 entries now. But the number of independent parameter remains n plus m minus 2. Clear what is happening? So it is happening because of this decomposition that you can do. It is only happening because of this decomposition. Okay. Now let us take one case where n is equal to 1000, m is equal to 1000. So what is the number of parameters? 100,000 or 1000, sorry, 1 million, right? Yeah, 1 million minus 1, right? 1000 times 1000, 1 million minus 1. So that is 9,99,999. And if they are independent, then what is happening? 999 plus 999, which is somewhere around less than 2000. So you can see the drastic reduction in the parameter that can happen. Correct? It is quite obvious that in high dimensional problem, if you can assume things to be independent, the number of parameters will reduce significantly. Correct? So this is why checking for independence is very important, because if you are not checking for independence, you will try to figure out those 9,99,000 parameters. Whereas if you can first figure out if they are independent or not, you will work with 1800 parameters or so, 1900 parameters. So that is why this independence is very important, and you will later see in this course when you go into this surrogate modeling business. There is one topic that I will try to cover is sensitivity analysis and also finding out independence. There are two things. Sensitivity is whether it is sensitive or not. If it is not sensitive, these parameters will not, the variable itself will remove. And then if they are independent, then okay, that is the best case scenario, our parameters will reduce. So that is why remember that in many a times, even when things are not independent, and they are loosely dependent, we still assume them to be independent, because that makes the problem tractable. Okay, that makes the problem tractable. Okay. So this independence is very important. It will come back again and again, along with this sum and product law. These things will come back again and again, not in the initial stage of the course. Initial stage will focus on Taylor series, but they will start coming back as we go to sampling and then surrogate modeling, then system reliability, time dependent reliability. Everywhere this concept will come back. So this will be present and scattered throughout this course. That's why I am kind of reviewing it. Okay.
So
Yeah.
do we just assume independence at the starting, or do we do some sort of test before assuming independence? Because otherwise,
Both thing. So
result in the loss.
both thing. So there are some models which works based on this assumption. There is a model known as naive Bayes. So naive Bayes algorithm works on the assumption that things are independent. So now that is one part of the answer. The other part of the answer, then you should be check whether naive Bayes is even applicable to your data set or not. So that's where the testing part comes into picture. So people have developed models based on assumption, and then it is your job to ensure that whether that model is even applicable for your problem or not. Okay. So there is a very popular saying, right? All models are wrong, but some models are useful. And that is true not only in this, even in mechanics. Plane section remains plane before bending, remains plane after bending, right? That is an assumption. You can use that assumption with Euler-Bernoulli beam theory. So you should first check whether the beam is slender or not, how much deformation is going on, and if you see it is within those criteria, now you bring that Euler-Bernoulli and then apply. If it is not, then you should use the classical stress equilibrium in 3D or whatever, and then solve with every details without any assumption. And even then you will assume the constitutive relation, by the way. So, that you cannot let go of. You cannot let go of assumption, but yeah. So, the important point is that, to answer your question, we do both. There are some models which are developed based on this assumption, and then it is your job as a user to test before using those models. If you use them blindly, then it will not give good result, as simple as that. Okay. So, I will stop here. Next lecture, which is day after tomorrow, we will start with random variable, what is random variable, and review the different distributions, and along with mean, moment, the moments, mean, variance, standard deviation. So, basically I will try to wrap it up in the next lecture. I find this review quite boring if you know it. If you do not know it, then it is useful, obviously. So, I want to start the reliability, real reliability part ASAP, but this is actually important, so I have to review it. So, next lecture will basically, starting with random variable, we will try to wrap things up, PDFs, PMFs, CDF, moments of PDF and all those things, and yeah, so then we will start with reliability, not in next lecture, but maybe the one after that. Okay.